Remote sensing is a fascinating term for any technique that allows us to take measurements at a distance without needing physical sensors placed directly at the location being studied. There are many techniques out there, with more being developed all the time, but today we are going to focus on the heavy hitters: radar, atmospheric sensors, and satellite imagery. To start off, let's take a closer look at how radar images are generated and, more importantly, how we can interpret them to gain a real advantage in the cockpit. At its heart, radar works on a simple principle. A transmitter sends out a pulsed beam of electromagnetic radiation, and a receiver waits to record any signals that reflect back. Weather radar is specifically designed to detect precipitation, but it's important to know there are two distinct types. Standard weather radar tracks the location, extent, and intensity of precipitation, while our newer Doppler radar takes it a step further by also detecting the lateral motion of those precipitation particles. Here's how we find our distance. The time elapsed between sending the signal and receiving the return echo is directly proportional to how far away that precipitation is from the radar unit. Reflectivity, which is essentially the amount of power reflected back to the unit, tells us exactly how intense that precipitation is. You can even estimate the type of precipitation based on those reflectivity readings. As a general rule of thumb, the heavier the rain, the stronger the returning signal will be. You'll usually see rainfall radar displays presented in various colors to show different intensities, all overlaid on a map for easy reference. Typically, blue represents light rain, while those bright yellows and reds indicate much heavier precipitation. While it's easy to look at a radar picture and spot precipitation and its movement, it can sometimes be tricky to distinguish between a true precipitation echo and one that isn't. The most frequent non-precipitation return is a ground echo. Since the ground doesn't move, it's actually quite straightforward to filter those out of the picture. However, keep in mind that precipitation can sometimes fall in the shadow of high ground, meaning it might remain invisible to the radar. Another phenomenon we encounter regularly is what we call anomalous propagation, or ANAPROP for short. As the radar beam travels through the atmosphere, it naturally curves downward due to vertical variations in atmospheric density. Because the beam travels faster in thinner air, in extreme cases where the air near the surface is very cold and dense, a beam aimed upward can actually be bent all the way back down to the ground. You'll see the same effect when there is strong static stability in the lower atmosphere. The diagram shows a classic setup with a temperature inversion and a sharp hydrolapse in the bottom few thousand feet. Within that inversion layer, the radar beam is refracted downward compared to its initial path. The combination of these effects results in a noticeable increase in ground clutter on the radar display, as you can see here. This typically happens under anticyclonic conditions where a deep nocturnal inversion forms near the surface. In this particular example, those echoes are caused by reflections from the surrounding hills. If you have access to data from multiple radars, identifying ANAPROP becomes much easier since neighboring radars generally won't display the same false echoes. You can also cross-reference the radar imagery with surface observations or satellite data to see if precipitation is actually occurring, which helps you quickly rule out ANAPROP. Sometimes, interference from external radiation sources can lead to errors. A great example of this is the sun. If the radar happens to point directly toward the sun during sunrise or sunset, the reflectivity pattern might display a ray of strong echoes extending outward from the radar site. In this example, the spike appearing to the west-southwest is actually caused by interference from another transmitter. Interestingly, local wildlife can sometimes create some pretty strange and unexpected radar returns. For instance, when you see echoes from large flocks of birds or massive insect swarms. It's standard practice to view a radar composite or mosaic image to cover a wider area. Since each individual radar typically has a range of about 100 to 150 kilometers, we piece several of them together to give us the big picture of the weather. Often, these images are presented in a movie loop, which allows us to track the development, speed, and direction of movement of the weather systems. Next up, let's explore a form of remote sensing called atmospherics. This is a clever technique used to pinpoint areas of lightning and active thunderstorm development. As we've discussed many times throughout this course, thunderstorm activity is a serious hazard to aviation. Beyond the danger of lightning strikes, we have to watch out for associated threats like severe icing, intense turbulence, wind shear, and heavy precipitation, especially hail. So, being able to remotely identify these storm cells in data-sparse regions allows us to map out exactly which areas we need to avoid to stay safe. This tool is also a fantastic resource for forecasters, allowing them to provide early warnings to individual airfields or ATC whenever a thunderstorm is approaching. The most widely used system for this is known as ATD, which stands for Arrival Time Difference. Way back in the early 1920s, it was discovered that when a lightning flash occurs, it emits radio waves across a broad frequency band. We refer to these as atmospherics or simply spherics. You might have even encountered this yourself as static interference while listening to your radio. An ATD system determines the precise location of a lightning strike by measuring the time difference of the atmospheric signals arriving at various pairs of detector stations. By comparing these times, the system triangulates the exact origin of the lightning. As you can imagine, this requires incredibly precise measurements. The system actually uses atomic clocks to keep all the detection stations perfectly synchronized. The ATD system used by the UK Met Office is fully automated, and thanks to recent upgrades, it can now locate lightning at a rate of 8,000 flashes per hour with better accuracy than ever before. Here is a satellite image of South America with ATD lightning data overlaid. It's impressive to see that even halfway around the world, the system remains accurate to within just a few kilometers. From these calculations, we generate maps showing lightning strikes. These maps are usually animated in time steps so you can clearly see how thunderstorm activity is developing and moving, with updates typically provided every 5 minutes.